Hey everyone! In the previous video, we had downloaded a number of network datasets in different formats. In this video, we are going to see how we can analyze them using Networkx package of Python. Let's take a look at the datasets that we had downloaded. So these are the datasets that we downloaded in the previous video. So we had 6 networks. We had a network in GEXF format. We also had a Facebook network in HList format. We had a football network in .NET format, which is equivalent to Pagic format. And we had a karate club network in GML format. We also had karate network in Pagic format. And we also had a Wikipedia network in GraphML format. So these were the 6 network datasets that we had. Now we're going to see how we can analyze them. So I have all the datasets in this folder. I'm going to create a new Python file here where I'll be writing all the code. So datasets.py. I'm going to open it in an editor. I'm using Sublime Text here. You can use any editor for that matter. Okay. Since we are going to make use of Networkx package, I'm going to import it. We are also going to visualize the networks, so I'm going to import matplotlib as well. Now let's take the first network. In this folder we have, let's make use of this Facebook combined.txt network, which is in edgelist format. Let me copy this name. So now since the Facebook network is in edgelist format, the function that we are going to make use of is read edgelist. So I'm going to write g is equal to nx dot read edgelist, and here I'm going to give the name of the network. Now our datasets are kept in a folder. I'm sorry, I think that's the name, _sets. Okay, so in that we have, this is the name of the network. So you see the function that we are using is read edge list function, which is present in Networkx package, and as a parameter we are giving the name of the network. Now this function basically takes the network in the edgelist format and returns a graph object, and then we can apply any function on this graph object. For example, if you want to look at the basic information of this network, we can write nx.info, and as a parameter we give g. So info is a function which provides the basic details as to the number of nodes, number of edges, etc. about a graph. So let's save this file, and I'm going to open my terminal here, and I'm going to run this file. So alright, so here you see, firstly it tells us the type. The type is a graph, as in it basically tells us whether it is a digraph or directed graph or it is a multigraph, and it tells us the number of nodes. It also tells us the number of edges and the average degree. So these are just the basic details about the graph. Now let's go back to our file and add some more things. So this is about the basic things. If you just want to get the number of nodes, you can write now nx.number of nodes is a function which returns you the number of nodes. If you have to just get the number of nodes, you can use this function. And similarly, if you want the number of edges, as in you don't want all the other information, you can use this. And in case you want to know whether the graph is directed or not, then you can make use of this function, print nx dot is directed. So as a parameter you pass the graph. So this should tell us whether the graph is directed or not. Let's go back and try to run this. So here you see, after the basic statistics, it told us the number of nodes and edges, and it's false, that is it is not directed. So this Facebook network, that was a friendship network, it's basically undirected network. So that was about how we can read an edge list network into a Networkx object. Now let us see the other kinds of networks that we have. We also have here .NET format. As I told you in the previous video, that .NET format is basically the PAGIC format. So in order to read this network into the Networkx object, we will use a PAGIC function. So let me show you how to do it. So what I'm going to do is, I'm going to use this function read PAGIC, which is a function that is used to read a .NET or .paj file. So let me check the name of the network, football.net. So change it. Okay, so I'm reading this .NET network through this function read PAGIC into a graph object G, and then I'm applying all these operations. Let's see when we run this. So here you see that the type of the graph is multi-digraph. That means there are multiple edges between the nodes, and it's also a directed graph, and it's telling us the number of nodes, number of edges, and since it is a directed graph, it's telling us the average in degree and average out degree, and after that again it's giving the result of the functions number of nodes, number of edges, and it's true, which means it is a directed graph. So these were just the basic functions. Let's see what other kinds of networks do we have. We have a GML network, we have a PAGIC format as well. Okay, let me show you that for reading the PAGIC files as well, you use the same function, that is read PAGIC. Okay, so the network name is karate.paj, so I'll replace this. Okay, so when I run this, I'm getting that this is a multi-graph. Okay, and the number of nodes are 34, number of edges are 78, and this is the average degree, and it's not a directed graph, so we're getting false here. Okay, now two more network formats that we have are GraphML and GEXF. So let me show you quickly show you how we can read them as well. Okay, so GraphML, how do we handle it? Okay, the function that we'll use it, read GraphML, and the file name is wikipedia.graphml. So this is how you will use it. Okay, since this is redundant information, I'm going to comment this. Okay, now let me run this. Alright, so what we're getting here is that it's a digraph, Wikipedia, because this is a graph between the nodes are the articles. It basically tells us whether an article is referred to in the other article or not. So it's basically a directed graph. 921 are the number of nodes, number of edges are given, and since it is directed, we are getting in degree as well as out degree, the average in degree and out degree, and it's true, that means it is a directed graph. So let's go back here, and the only format that is left is GEXF. Let me quickly show you how to convert into a graph object as well. I'm copying its name, and here let's go back. Sorry. Okay, so since this is a GEXF format, we'll make use of function read GEXF. And what's the name of the function? Let me rename this so that it doesn't create any problem, and let me rename this as well. Okay, so it should work. Let's see. So this is how we can read various networks in different formats and convert them into a graph object. Once they're converted into graph object, we can apply various functions on them and we can play around with them. Now let me also show you how we can visualize a network in Networkx package. So let me take a small network. Let me take Karate network itself, and we had it in GML format. Oh, I think we haven't added it. Okay, we can quickly add it. So the function is read GML. So if you have a graph which is in GML format, the function that you will use is nx.readGML. So okay, all right. So we read a karate network which was in GML format. We made use of function nx.readGML. So let's execute this program. Okay, so this is a simple graph and these are the number of nodes and edges, and it is an undirected graph. Now let me show you how we can visualize this graph. I'm going to comment this. I'm going to comment this as well. Now the function that we'll use to visualize the graph is nx.draw, and the parameter will be the graph that we have to draw. In order to see that graph, we have to use this function plt.show, basically the show function which is available in matplotlib. So that is how we'll be able to see this graph. Okay, now let me run this. Alright, so this is our graph, the karate network, and the labels are given here. Let me also show you a few features that this interface provides. For example, this when you click this, you can just move the graph the way you want, and the next option is zoom to rectangle. So when you click that, if you want to carefully observe some part of the graph, you can just zoom it and see, and if you further want to do that, you can do the way you want, and then you can go back, and then you can go back. So these are a few functions that a few features that you can make use of. And this is configure subplots. This will be used when we plot something. This is just a graph. I'll show you the functionality of this later. Then this is how you can save the figure. Okay, let me close this window now. Let me go back to the program. Let me also show you how a directed graph in Networkx looks like. Since this karate is an undirected graph, let me comment this, and if I am not wrong, this football network was a directed network. So I'm doing the same analysis on football.net. Let me execute it again. You see, this is how a directed graph in Networkx looks like. So you see the arrows are represented like this. If you want to zoom it, again you can make use of this feature. You want to zoom this area, you can further zoom it as well. So this is how you can closely analyze whatever you want in the graph, right? And you can then go back, or you can just press home here. Okay, then you can save the graph as well. Okay, let me close this now. Okay, I'm going to continue the rest of the analysis on karate network, so I'm going to uncomment it back. Let me also show you that there are different layouts which are available in Networkx. For example, we have as of now used this function nx.draw. We can use another function if you want a different layout. So we can use nx.draw circular. Okay, so this is one of the layouts. There are various layouts available. Let me show you the output that we get in this case. So here all the nodes are arranged along a circle, and the edges between them are shown like this. So this is called circular layout. There are a number of other layouts as well, for example spectral layout and string layout. So you can just read the documentation about them. So we have visualized the network. Let's close this and let's go back to our program, and we can do some basic analysis on this. One of the things that we can check on this network is we can check the degree distribution. Now, what is degree distribution? Degree distribution basically tells us how many nodes are there in the network that have a particular degree. So this is done for all possible degrees that a node can have in the graph. Let's take this example graph. So here, how many nodes are having degree 1? So node number 4 and node number 9, they are having degree 1. So corresponding to 1 will have 2, and similarly we can check how many nodes are having degree 2, how many nodes are having degree 3, 4 and 5. So these are all the possible degrees that nodes can have in this graph, and corresponding to the degree we have the number of nodes that have that particular degree. So this basically is called the degree distribution of the nodes in a graph. Now, it is always a nice idea to plot the degree distribution to get a better idea of the graph. So when we plot this, we get this kind of distribution. So on the x-axis, we maintain the degree, and on the y-axis, we maintain the number of nodes that have that particular degree. So this is the kind of plot that we get for this example graph. We can check for our data sets what kind of degree distribution do they exhibit. So let's go back to our program and let's try to check what kind of degree distribution this karate network has. For that purpose, I'm going to create a function to plot the degree distribution of this graph G. So let me create a function here. Okay. Before we implement this function, I want to show you a few things on the IPython console. So let me copy this and let me open the IPython console here. So basically I just copied those first two statements here, and let me also copy this statement here. Okay, so we have the karate network in the object G. Now, if I want to see the degree of each node in this graph, I can make use of this function nx.degree G. So what this function does, this degree function, it basically returns a dictionary where the key is the number of the node and the value is the degree of that node. So here we get the dictionary for all 34 nodes. We are getting the degrees of these nodes. Now let's go one step back and recall what is our aim here. Our aim is to have the degree distribution of nodes in the graph. So basically we want that for a particular degree, how many nodes are there in the network that are having that degree. So we basically first of all want to get the possible degrees that the nodes are having in this network. So we are getting the dictionary here where we are getting all the possible values of the degrees that the nodes can have. So what we are interested here in is basically the values. So what I can write is nx dot degree G. So this is going to give me a dictionary. All I'm interested in is the values. So I'm going to write dot values here. So it should return me a list which is having all the values. So what I get here is basically all the possible degrees that the nodes are having. Now my aim is to get the possible degrees that the nodes can have. Here you see there are a lot of repetitions. So I want to get the unique degrees. So in that case, what I can do is I can just write all this inside a function set. So what it will do is it will convert the output into a set, and we know that in set there cannot be any repetitions. So what we get is the unique values, basically the unique degrees that the nodes can have in this particular network. Now, list is more flexible a data structure as compared to a set because we can perform a lot of operations. So I can further convert this into a list if I want. This is basically up to you how you want to handle the data. So I converted this into a list. Now what I get finally is a list of all the unique values of degrees that the nodes can have in this network. So I showed you here so that you can see what's going on in the function. Now let's get back and use these functions in the function that we were creating. So firstly, I want all the degrees, so I'll write nx dot degree g. I want all the values only, I don't want the dictionary, so I'll write dot values. So here I get all the degrees. Let me comment all the degrees. Now I am also interested in getting all the unique degrees so that I can see what are the possible degree values. So what I'm going to do, the same thing that I did on the console, I'm going to pass all degrees here. Okay, so here I get all the unique degrees. Now to get the degree distribution, what I basically want is I want to, out of all the values that are there in this list, unique degrees, I want to see how many nodes are having that particular degree. So basically what I'll do is I'll fetch one element out of this list, that is unique degrees, and I will see how many occurrences of that value are there in all degrees, right? So probably I can start a for loop here. So I'll write for I in unique degrees for I. So what I want to check is how many occurrences of I are available in all degrees. So I can start a variable, probably x is equal to all degrees dot count. So we have this function count in a list which tells us the occurrence, number of occurrences of a particular element in that list. So x will be telling us the number of occurrences of the degree I in the list all degrees. So probably we can keep a track of all these values. So we can create another list, count of degrees. I started an empty list, and so I'm going to append the x values to this list. So basically the occurrences of the first degree are now stored in the list count of degrees. So after this for loop is finished, we will have all the degree distributions in this list that is called count of degrees, and then we can plot it. So let's try plotting it. So plt.plot, as you might be knowing, there are two parameters that have to be passed here. So on the x-axis we want all the unique degrees, and on the y-axis we want how many nodes have that degree, which we have stored in count of degrees. So we'll pass that here. So let's try plotting it. So I'll write plt.show. Okay, we haven't called this function yet, so let me call this function here, and I'll comment this. So I'll call this function plot degree distribution, and I'll pass this g here. Okay, let's go back here, not here, we'll go, okay, we'll try running this. Okay, so this is the degree distribution that we are getting for the karate club network. So this is the x-axis where the possible degrees are there, and on the y-axis the number of nodes having that degree are there. And you can just again play around with this plot. As I told you, you can just use this to move the plot, you can use this to zoom a particular part, and you can just go back as well. And this is a feature that you can use here. Basically you can just increase or decrease the x and y margins. So this is up to you, whatever way you want it, and you can always reset it as well. So let me close it. So this is basically up to you how you want to visualize it. Okay, let me close it. There was no x and y axis, as you see, so we can do that. So let me just quickly do that. Before that, you can also change the way this plot is appearing. So if I put these dots, you will get the plot in the form of these dots. Okay, so you get yellow dots here, and you can also put a line here and dots as well, so you'll get both the things. So this is the plot that you're getting. One thing to observe here is that most of the real world networks exhibit power law degree distribution, which means that there are very few nodes which have very high degree, and there are a lot of nodes which have very less degree. So the same is being followed in this small network as well, apart from one exception of this node. So that might happen in some cases, but in general real world networks have this power law degree distribution. Okay, so let's go back and add a few more things. Maybe let's add the X label. So let's add degrees here, and then we can add the Y label as well. Maybe number of nodes, and maybe we can add the title as well. uh, Degree distribution of karate network. So let's run this. Okay, you get the title and the X and Y label as well. So you can just use more features, more functions, and decorate this plot the way you want. There's one more thing that usually is done in case of power law degree distribution. We can also check the log plot of that. So how can we do that? We can just replace this plot by log. So in that case, it will give us a log plot, which basically means it will take the log of x-axis, it will take the log of y-axis, and if a network is following complete power law, the log plot should be a straight line. So let's see what kind of plot do we get in this case. So here, firstly, we had an exception here. Secondly, it was in perfect power law, so we have this kind of line which is not exactly straight. So this is the kind of log plot that we are getting in this case. So this was about the degree distribution. Now I'm closing it. Let's go back here and see some more properties that we can analyze on this network. We are done with degree distribution. Let's go ahead. So next thing that we can check is density. Density value of a graph basically tells us whether it is a sparse graph or it is a dense graph with respect to the number of edges present. So if there are n nodes in a network, the total possible edges that network can have will be n choose 2. Out of these n choose 2 edges, what is the fraction of the edges that are present in the graph is basically what is told by the density value. So if it is a simple graph, the density value will be between 0 and 1, and if it is empty graph, the density will be 0. If it is a complete graph, density will be 1. However, if it is a multi-graph where more than one edges are allowed between two nodes, in that case density value will be more than 1, can be more than 1. For example, in this diagram you see a simple graph with 9 nodes. So the total possible edges that can be there in this network will be 9 choose 2, which is 9 into 8 divided by 2, that is 36. Now the number of edges that are present actually in this graph are 11. So the density is going to be 11 divided by 36, and that is equal to 0.31. So the graph is not very dense. So this is the kind of indication that the density value gives us. So we can go back to the console and see the density value for a few networks. For example, let me go here and let's create, okay, let me clear this first. Let's create a complete graph. So I'm going to write G is equal to nx dot complete graph of say 100 nodes. Okay, so since it is a complete graph, what should be the density value? Let's check nx dot density. So this is the function density which is available in Networkx, which will give us the density value. Obviously in case of complete graph it is going to be 1. Let me now create another graph. Let me keep it empty, nx dot graph. So I haven't added any edges into it. Let me add a few nodes here. So I'm going to pass a list. So I'm passing only 4 nodes. Let's check the density value of this network. So since we have not added any edge, obviously the density value was going to be 0. Now let's go back here and see what is going to be the density value for our network, karate network. So what I'll write is print density is, so nx dot density, and I'm going to pass g here. Let's go back, check here. Density is 0.139, so basically it's sort of a sparse graph, that you can check. So that was about the density. Let's go back and see a few more things that we can check on these networks. Next, you can see clustering coefficient. So for a given node, clustering coefficient basically tells us the number of links that are present amongst the neighbors of this node with respect to the total number of links that can be possible. I'll show you using an example. Let's take this network. Let's try to find out the clustering coefficient for this node 6. So as you can see, this node has 5 neighbors, right? These are 1, 2, 3, 5 and 8. So there are 5 neighbors. So what we have to check here is the number of links that are present amongst these neighbors. That is the number of links amongst 1, 2, 3, 5 and 8. As you can see, we see only one link that is there between 2 and 3. There is no other link present amongst these neighbors. So on the numerator we'll put 1, and on the denominator we'll put the total possible links that can be there amongst these 5 nodes. So amongst 5 nodes, total possible links can be 5 choose 2, which is 5 into 4 divided by 2, that is 10. So in this case, the clustering coefficient of this node 6 will be 1 divided by 10. So in case of a friendship network, this clustering coefficient basically tells us how closely knit the friends of a particular node are. So we can calculate the clustering coefficient value for every node, and then we can find the average as well. So average clustering coefficient further tells us the amount of clustering present amongst the nodes in the graph. So let's go back and try to check the same for our network. So I'm going to comment this. The function that we can use for finding the clustering is nx dot clustering. However, this function basically returns a dictionary which gives the clustering coefficient value for every node. So you can always iterate over this dictionary. So what I'll do is, for I in nx dot clustering G. So I am interested in all the items, so I'll write dot items. I want to print I. So I'm going to comment this. So what we are doing here is this nx dot clustering is returning a dictionary which contains the clustering coefficient values for all the nodes. We are just going to print them. So let's run this. So we are getting this dictionary where for every node we are getting the clustering coefficient value. So if we want the average clustering coefficient, we can either average these values, or we can directly make use of another function which is nx dot average clustering. So this should tell us the average clustering present in the network. So you see 0.57 is the average clustering. So more this value, more the clustering, and more tightly knit the people in the friendship network are. That was about the clustering coefficient. Let's go back and check a few more properties. So what is the diameter of a network? Diameter is basically the maximum shortest path that we have to travel to go from one node to the other. For example, if you know about all pair shortest path algorithm, it basically returns a matrix where the values are the length of the shortest path between the two nodes. So it does that for every pair of the nodes. So whatever is the maximum value in that matrix will be the diameter of the network. In other words, it's the shortest path between two most distant nodes in the network. So, for example, if you see node 1 and node 9, so if you have to go from 1 to 9, you would have to traverse this path 1 to 6 to 5 to 9. There is no other shortest path between them. So, the length of this path is 3, and we don't see any other shortest path which is longer than this 3. If you want to go from 1 to 4, again the length of the path is 3. If you want to go from 3 to 9, the length is 3. So we don't see any other shortest path which is more than 3. So that's why the diameter of this network will be 3. We can check the diameter of our network here as well. So I'm going to comment this and let's check the diameter. So I'll write diameter is, so the function that we can use is nx dot diameter g. So it should give us the diameter. So diameter is 5. So there are 34 nodes here and the diameter is 5. It's basically observed that in real world networks the diameter is basically very less, because the nodes are connected to each other, and that makes the distance between them very small, and that's how the diameter reduces. So these were just the few points of analysis that we performed on the networks that we downloaded. The main thing to note is here is that once you get the network in the Networkx graph object, you can just play around with it. You can apply all the functions that are available. You can just read the documentation and apply the functions which are relevant for that network, and you can go ahead with your analysis.